Welcome. This is Fundamentals of Micro and Nanofabrication. I am Swayam from IIT Bangalore. Today we shall continue the module on subtractive manufacturing, and we shall look at specific recipes of wet etching. So let's get started. To some extent I discussed this in the previous lecture, but this is a prototypical wet etching reaction. So what is happening is you have a film, you have an etching mask. This can be photoresist or it can be a hard mask, that doesn't really matter. Now, in order to do the etching, three things must happen. You must have an etchant, and that etchant is probably there in the bulk of the solution, and it's possibly due to agitation or due to flow, there is some churn there. So that's what this arrow represents. Now, this fresh etchant must reach the etching, the film being etched in order to do the chemistry. So it must go through a layer. We are calling it a stagnant layer, and the reason for that will be obvious in a minute. Then once it reaches the surface, then it must react, it must form a byproducts, and those byproducts must again go through the stagnant layer back to the bulk of the solution, right? And this process must continuously be happening in order to get a consistent etch rate. Now, why is there a stagnant layer? Now, those of you who remember the CVD lecture would see the parallels. We sort of discussed a very similar looking reaction mechanism when we were doing deposition. And the reason for the stagnant layer is essentially the same. In any system where there is a source and a sink, often there is always a problem of how do you actually transport the material. Now, in absence of active flow, the way the material transports is through diffusion, and that diffusion must happen through the stagnant layer, where is this just a lot of where it's just an accumulation of byproducts, but very low concentration of the fresh etchant. So the fresh etchant must make its way through this layer of byproducts in order to get to the surface. You always have this stagnant layer, and something similar must happen when the byproducts leave the surface. You have to encounter the stagnant layer in order through which you must diffuse. Now, if you have agitation, if you have stirring, then the stagnant layer can be broken up a little bit, and that means that your etching rate can be a little higher. But even in those cases, there's always a microscopic layer of junk that you have to diffuse through before the fresh etchant can actually reach the surface. Now, once it reaches the surface, you always have to worry about the chemistry that you are actually doing to do the etching. The reason this can be important is that the byproducts must be volatile. If you are etching silver and the byproduct that you are forming is silver chloride, which does not dissolve under water, then that is not a good etching recipe. A good etching recipe would always form soluble byproduct, right? And that soluble byproduct will then make its way through diffusion back into the solution. The other thing you have to worry about is selectivity. A lot of times you are doing the etching through an etching mask, so there must be some selectivity in the etch. If there is no selectivity in the etch, then that really restricts the amount of the depth of which you can etch, something that we discussed in the previous lecture. So once again, just like in CVD, the kinetics decides whether you are in one or two cases. It is possible that your surface reaction rate limited, which is the step number 2, or it is possible that your diffusion rate limited, which could either be bottleneck is step number 1 or step number 3. Okay. Now, in surface reaction rate limited, the slowest step is the one where this reaction actually occurs on the surface. So this flux is actually slower. And since both the diffusion flux and the reaction flux must be equal in equilibrium, the rate at which the etching can occur is decided by the rate at which the reaction can occur and not limited by the diffusion. So that is the surface reaction rate limited. However, sometimes the surface reaction rate is very fast. If the surface reaction rate is very fast, then you are always waiting on fresh etchant to get to the surface, and in that case you are in the diffusion rate limited regime. Now, as we have discussed during CVD2, surface reactions or chemical reactions are often very strongly dependent on temperature. So, if the etching rate is surface reaction rate limited, then you can expect temperature to play an outsized role in the etching rate. Typically, the etching rate can go up to 2 times for just 10 to 15 degrees heating of the solution. And the advantage with this is you can probably etch at higher rates. The disadvantage of this is that you often have to worry about selectivity. You sometimes have to worry about degradation of the resist material that you are using to pattern. You sometimes have to worry about non-uniformity. It's one thing to say that I'll heat the solution by 10 degrees, it's quite another to ensure the solution is uniformly heated by 10 degrees everywhere. Simply putting a solution on a hot plate does not always achieve that. If you are diffusion rate limited, often stirring and agitation tend to have an effect, because these are two things that will make the diffusion go faster and slower, and depending on how much stirring and agitation you do, your etching rate can be slightly different. The advantage again here is that this provides you a method to make your etching rate faster. The disadvantage is that non-uniformity might crop up. It's very hard to get stirring and agitation type effects be uniform across wafers, especially if the wafers are very large. If you have imagine you have a 12-inch wafer and you're trying to create an agitation by swirling the beaker, it's very hard to get the swirl of the beaker exactly right everywhere on the wafer, right? The movement of the liquid might be lower in the middle of a swirl, might be higher at the edge of the swirl, and that might start causing non-uniformities. Under what conditions is the surface reaction rate limited more probable? Under low temperature. Because at lower temperatures the reaction rate falls and then it becomes a slow step. If the etching is dilute, probably diffusion is not a problem, diffusion is fast, and if the diffusion is fast, then by corollary the surface reaction rate is slow and hence the limiting factor. For weak etchants by definition are etchants that do not react with the surface very fast, and if they do not react with the surface very fast, they are by definition reaction rate limited. Under what conditions do you get a diffusion rate limited regime? Typically at high temperature, because at high temperature the diffusion becomes fast, the reaction rate becomes faster, which often means now the slow step is the diffusion. Diffusion, as we have discussed, does not scale as quickly with temperature, diffusion through a film as quickly with temperature as surface reaction rate does. If you are looking at viscous and concentrated etchants, often they are diffusion limited, because through viscous and concentrated films the diffusion process tends to be slower. Something very similar happened in CVD, if you remember. Aggressive etchants, by definition aggressive etchants are those whose chemical reaction rate on the surface is very fast. If it's very fast, by corollary the diffusion is probably the slow step, and if the diffusion is probably the slow step, then you are diffusion rate limited. The surface finish in these two cases is often slightly different. As we have discussed, surface reaction rate limited often tend to be anisotropic. And why they are anisotropic? They are anisotropic because if you are reaction rate limited, the chemical reaction can be different on different facets of a crystal. 100 might be different from 111. There also the surface energies can be slightly different, and all of those factors change the etching rate. This leads to possible anisotropic, but it also leads to roughness. If you start with a smooth film, but different facets of the film are etching at slightly different rates, by the end of it you might see some micro roughening. Diffusion process, of course, do not depend on direction at all. By definition, diffusion is an isotropic process. It doesn't matter whether it's going laterally or vertically. And that means that it does not show any dependence on different facets. The reaction tends to be an isotropic one, but more interestingly, it leads to smooth, shiny surfaces, because there is really no difference on the micro and on the macro scale why diffusion would go in one direction more and the other direction more. So you always get these smooth films. So if the goal is to get smooth and shiny films, maybe you should move towards a recipe that is diffusion limited. If the goal is to get anisotropic etches, then maybe you want to move towards surface reaction rate limited regimes. Typically, the contamination in a surface reaction rate limited regime is low, and that is because the etching rate is always limited by this the etching process, and also because this often happens for dilute etchants. For dilute etchants, the amount of byproducts that are left over on the surface or the junk that is left over on the surface tends to be low. Diffusion rate limited recipes often are viscous, concentrated, very heavy etchings that often tend to leave a residue. So the contamination can be high. This is especially true if out diffusion is a problem, if step number 3 is a problem. This is also can happen if the byproducts that are forming by the recipe are not very soluble in the solvent or are not very volatile. Okay. Typically, the applications for surface reaction rate limited are cleaning. We spent a lot of time talking about cleaning, and in a very general sense, cleaning is nothing but etching. Etching where we are trying to do very little of etching, mostly trying to do just remove the contamination on the surface, but still it's an etching recipe nonetheless. So all the concepts of cleaning that we discussed do apply to wet etching too. Diffusion rate limited etching tends to often be actual etchants. If you want to, for example, make a 10-20 micron deep hole in silicon, you probably will not have a dilute solution. You probably will have a viscous, concentrated, aggressive solution, which tends to be diffusion limited. One comment on the general mechanism of etching. Now, right now we are talking about wet etching, so I'm using the words like solvent and diluent and etchant, etc. And this tends to create an expectation that we are only talking about chemistry. The fact is we are not just talking about chemistry, we are talking about electrochemistry. Most of the etching actually is an electrochemical process. Now, where does the electricity come here? It doesn't come here explicitly. It is not like we are actually supplying current or we are actually applying voltage. The electrochemistry comes in because the way the etching progresses, it creates domains of positive and negative charges. How are these domains formed? They're just formed because of perturbations. They form randomly. So, on a given surface, different domains, the domains would form, and these domains would change with time. What is positive right now may become negative down the line, and these different domains alternatively act as anodes and cathodes and do the etching reaction or the etching chemistry that actually leads to removal of the material. Only when you appreciate that this is an electrochemical process where positive and negative charges are playing a role, can you actually understand some of the second order effects of etching. For example, several etchants will show you a dependence on doping. Now, that is very hard to understand if it's completely a chemical process, because doping is less than 10 to the power is less than parts per billion. Why should an impurity parts per billion really change the etching rate of the bulk material? But if you understand this is an electrochemical process and doping changes the work function of the material, it's easier to understand whether the etching rate would be different or different doped films. Often defects in the semiconductor affect the etching rate. Again, this is very hard to understand if the defect is, say, a dislocation, which is not changing the bulk properties of the material too much. But if you understand this in an electrochemical process, then you can appreciate that maybe defects will have slightly different work function, will have slightly different bond energies, will have hence slightly different etching rates. This also complicates issues such as, this also further gets complicated because of issues such as temperature, impurity in the etchants, because the impurities in the etchant may act like surfactants, which will enhance the etching, but it can also be retardants, which will reduce the etching, and that becomes an important factor for selectivity, right? So, when we look at the specific recipes, I will highlight what is actually happening at the anode, what is happening at the cathode. But for the purposes of this slide, the bottom line or the take-home message is that always think of wet etching as an electrochemical process, not just a chemical process. Most etchants tend to be oxidative. If you remember the CVD lecture that we did, we discussed that there are different types of chemistries you can use to do a deposition. But the most common chemistry was always a reduction chemistry, and that was because most semiconductors tend to be reduced elemental semiconductors. If that is the case, it stands to reason that an etching process, which is a reverse of a deposition process, will probably be an oxidative process, right? So, most etches tend to be oxidative. The basic idea behind all of them is the same one that we did in cleaning. Depending upon what metal or what element you are talking about, it is either soluble in an acidic medium or soluble in a basic medium. And in cases if it forms an oxide that is insoluble, then you hope to create a complex, and that complex is then soluble and hence gets removed. So, the formation of complexes, whether it's acid/basic medium, is how you define a wet etching recipe, but most of them by and large are oxidative in nature. So, the canonical or the general mechanism is something like this. So, starting with a semiconductor, say M, you create oxide, say MOX, then you dissolve that oxide either in an acidic solution or in a basic solution or by creating a complex, and once it forms a soluble material, a soluble byproduct, that byproduct then out diffuses, goes away, exposing fresh semiconductor, and that fresh semiconductor again gets oxidized. So, this is the basic recipe, and we will keep using this concept and again as we go down this lecture. So, the most common etch the most canonical etch that we shall discuss is using hydrogen fluoride, which is an isotropic silicon dioxide etch. Now, the canonical example of wet etch that we shall discuss is using hydrogen fluoride to etch silicon dioxide. Now, some of you might find this familiar because even during the cleaning solution, we use dilute hydrofluoric acid to remove the chemical oxide that forms during the cleaning process. The difference is now we are actually looking at HF in a little more detail, and we are using it to etch thicker films of silicon dioxide, not just during cleaning. Hydrogen fluoride solutions are used to etch silicon dioxide. You can get hydrogen fluoride in 49% concentrated form. So, this is what you actually buy from a vendor. This is the concentrated HF as it is called. This is often diluted with deionized water because the concentrated HF is a very reactive solution, and for microfabrication applications it just etches way too fast. It is just very hard to control. So, you always take this HF and put the deionized water to dilute it down. Depending upon the proportion you choose, depending upon the dilution you do, you get different etching rates. The basic mechanism by which HF etches silicon dioxide is given here. So, silicon dioxide forms a complex with HF, which is H2SiF6, and this is a soluble complex. And this soluble complex floats away, leading to exposed silicon dioxide, and then fresh HF then attacks that fresh silicon dioxide, and the mechanism continues. The important thing to note is during this process, the HF actually gets consumed, right? So, if they consumed, then the concentration of the H plus ion also changes during this deposition. So, you can expect that the etching rate will change unless you put HF in remarkable excess. And this is a trick that we do in wet etching all the time. We are doing microfabrication after the films that we are etching are only a few nanometers. And even if you are etching it on full wafers, I urge you to do the math, you are trying to remove somewhere between micrograms to nanograms of material per minute. And at that low material removal, you do not need a lot of chemical. Again, if you do the math, it probably only requires a few ml of actual chemical to do the etching. However, you do not just put a few ml, what you actually do is take a whole beaker and put the wafer. And what that accomplishes is that you always have a plethora of etching solution, you always have a remarkable excess of the etching solution. And that remarkable excess of the etching solution means that even though you are consuming the etching solution, the absolute concentration of the etchant is not changing too much over the etching period. However, this assumption starts to break down if one, you do not have a lot of etchant, or B, you have a very dilute etchant. So, during cleaning, for example, we were using 1:100 or 1:50 diluted HF. In those cases, you have to start slightly worrying about how much is the concentration of your fluoride or hydrogen fluoride changing. One way to completely remove this effect from the picture and get much more reproducibility is to use buffer solution. Now, I urge you to remember your physical chemistry from 12th standard. There are certain solutions which maintain pH, and typically those solutions were, supposing you want to maintain an acidic solution, then you always put a salt of a weak base and a strong acid, and when you do that, you form a buffer solution where the pH is always maintained, the acidic pH is always maintained at a certain level. We do something very similar here for very similar reasons. Here the goal is not to maintain the pH because we want to maintain the pH, but because we want to maintain the concentration of HF such that the reaction with silicon dioxide remains consistent. So, what we do is to the HF solution we add a little bit of ammonium fluoride, which is a salt of a weak base and a strong acid. And the specific details you can always get from a physical chemistry book, but if you put in the right amount of ammonium fluoride, you can maintain an arbitrary concentration of H plus in the solution. And this H plus maintains at a certain level despite getting consumed during the reaction, because the ammonium fluoride starts to ionize and makes up for any loss in H plus. Typically we use the concentrated HF with around 40% ammonium fluoride in again various proportions. You tend to not use the concentrated solution, you tend to use diluted solution. This composition is what is called buffered oxide etch. So, if you ever find an etching solution in the clean room that says BOE, now you know what that means. Okay. The good news is that for all BOE solutions, the etching rate tends to be uniform even if you are doing long etchings. Okay. That is very important. Now, why is it called buffered oxide etch and not just by the chemical name? And that is because Buffered oxide etch also contains surfactants. The surfactants help in reducing the loading effect that we talked about when we were discussing uniformity. So, sometimes because of surface tension, especially in wet etching, sometimes because of surface tension, the liquid may not be able to penetrate a hole in order to do etching. Adding a little bit of surfactant solves that problem. You are able to reduce the surface energy, and the chemical is able to, the etchant is able to enter even small holes, up to, of course, a level. But the addition of these surfactants, which is essentially improving the wettability of silicon, does complicate the chemistry a little bit. So, often what happens is you buy a buffered oxide etch with unknown surfactants, but so the chemist would not give you the detail of the surfactant because that's a trade secret. But overall, if you get an etching solution from a reliable vendor which is experienced in making etchant solutions for semiconductor fabrication, then you just trust that everything is pure and the chemistry will work, and they give you what is the etching rate, and you just trust those numbers. Okay. Now, for any etching solution, you need a masking layer. What is the masking layer for hydrogen fluoride when you are trying to etch silicon dioxide? The masking layer is silicon itself. The great advantage of hydrogen fluoride is that it etches silicon dioxide fairly well, but it does not etch silicon. During cleaning, we did discuss some of the second order effects that can happen. For example, we discussed that if you leave exposed silicon and hydrogen fluoride for a very long time, it will not etch it, but it might roughen it. So, those kind of things can still happen. However, by and large, silicon is an excellent masking layer for silicon dioxide, which is another way to say the selectivity of silicon to hydrogen fluoride is very, very high. The etching rate of buffered oxide etch or HF, they are essentially the same thing, changes with concentration, and this is not hard to imagine. If you have a very concentrated solution of HF, you have more fluoride, more hydrogen ions, and that will attack the silicon dioxide better and hence create more etching. The good news is that this dependence is linear and hence very predictable. So, if you look at the etching rate at room temperature, which is where silicon dioxide etchings are commonly done at, and you plot it versus the concentration of HF. So, this is something we touched on during cleaning procedures. In semiconductor, we don't tend to use typical concentration measures like molarity or normality. We tend to use just proportions. So, for example, 1:100 HF solution means that there is 1 part of concentrated 49% HF and 100 parts of deionized water. So, for using this, you can actually back calculate what is the actual percentage in terms of weight, but that is not what typical semiconductor journals would report. You can also do the same dilution in 1:10, where there is 1 parts of 49% concentrated HF and 10 parts of deionized water, or you can do this in 1:1. So, as you go from 1:100 to 1:10 on this log scale, you find that the etching rate just linearly increases. From here to here, the etching rate will vary over 100 times, which is fairly easy to manage. The other thing to notice is that the etching rate does depend on temperature. This is something I hinted on in the last lecture, where in days of dilute where your surface reaction rate limited, etc., you often have some temperature dependence. So, at high temperature, you will get higher etching rate. So, this is the etching rate for the buffered oxide etch, a commercial buffered oxide etch from J.T. Baker. And so, compared to 20 degrees C at 50 degrees C, you are getting a much higher etching rate. Sometimes the etching rate increases can be in several times. So, from here to here, the etching rate has increased by 7 or 8 times, or for just 20 to 30 degree change. Now, this also highlights a fundamental concern, which is that temperature must be very tightly controlled if you were to get uniform etching. Very small changes in temperature cause large changes in etching rate. And of course, these curves shift upwards if you add more fluoride concentration. So, the 1:5 will etch much faster than 1:50. The next canonical example we shall discuss is silicon nitride etch. Now, silicon nitride can also be etched with just buffered oxide etch or hydrofluoric acid etch, but the etching rate is much slower than silicon dioxide. For example, it's only 0.5 nanometers for every minute for a high quality silicon dioxide layer, for a high quality silicon nitride layer. If you remember the lecture on deposition, towards the end we discussed the various methods through which silicon dioxide can be deposited. In that discussion, we looked at several properties of silicon dioxide through different depositions, density, refractive index, etc., but we also looked at etching rate. And in that I had made a comment that the better the quality of a film, the slower the etching rate. So I'm just restating the same concept here. And for higher quality films, the etching rate tends to be slower, and for silicon nitride using hydrofluoric acid, that rate is as small as 0.5 nanometers a minute. So even if you're just etching 10 nanometers, you can do the math, it will take you 20 minutes. That's a fairly long etch. It turns out photoresist is not a good masking layer. And the reason for that is because of the very long etch times. The etching rate is so slow that for practical cases, the etching times tend to be very long, and for those very long etch times, the photoresist does not hold up very well, and that leads to problems. To prevent all of these issues, oftentimes silicon nitride is etched through a different acid. It's etched with boiling H3PO4. Now, the challenge with the boiling H3PO4 is photoresist does not withstand this very well. So often the masking layer for this etch is actually a silicon dioxide. So this is an example where you're using a hard mask. Whenever you're doing patterning using photoresist, what you are using is a soft mask because photoresist is a soft material. But sometimes during etching you need a hard mask, which is you need, say, a silicon dioxide mask, where you first have to pattern the silicon dioxide on top of the silicon nitride, say using hydrofluoric acid, and then use the patterned silicon dioxide as a mask to etch the silicon nitride. So that is what you have to do if you have to use boiling H3PO4. When you use that, the etching rate tends to be a little higher. It is around 10 nanometers per minute for silicon nitride. H3PO4 does also etch silicon dioxide. So it does etch silicon dioxide at say 1 to 2 nanometers per minute, but that simply means you have a selectivity window of around 5. So if you want to etch say 100 nanometers of silicon nitride, you have to make sure that the masking silicon dioxide that you are using is at least 20 nanometers. In order to be a little safe, maybe you want to keep it at say 40 nanometers or 50 nanometers. However, in wet etching, a common feature is that the etch rates can often vary wildly. No matter how well known a recipe, HF, H3PO4 are fairly well known etches, but even then, different labs get slightly different numbers. And the reason for that is that different labs etch films of different quality. Saying that I have a silicon dioxide that is thermally grown means that it is of good quality, but of good relative quality. Maybe the silicon dioxide that is being grown in an Intel fab is of a higher quality than the silicon dioxide being grown in an academic lab, and that would lead to a change in the etching rate. Oftentimes, there's deposition method differences. A lot of the times people say, I deposit silicon oxide and I etch silicon oxide and this is the etching rate, but the details of the deposition process are hidden or often not reproducible. So once again, supposing I deposit silicon dioxide using PECVD, I can deposit under various conditions of PECVD, and those different conditions will give me different types of silicon dioxide, which will change the etching rate. There is the fixed DFT temperature. India tends to be hot. In an unregulated clean room where the temperature is not tightly controlled, you can expect a higher etching rate than, say, a lab in the US, which is at a higher latitude and is colder. There are also impurities in the layer. This is a very important case. So we discussed contamination policy, right? That how when you're doing deposition, we have to be very careful about impurities. Each tool allows a subset of impurities, but not all of them. So depending upon what subset of impurities a tool allows, it will have certain different impurity levels. And since this is an electrochemical etch, impurities matter, even trace impurities matter. And those trace impurities may change the etching rates. Here are two examples just to highlight the discussion that we just had. So supposing you are using an etchant which is 1:1 buffered oxide etch or buffered hydrofluoric acid. If you were to etch PECVD silicon nitride, which was deposited at 450 C, you would actually get an etching rate of around 300 nanometers a minute. Compare this to a thermal oxide, a high quality thermal oxide that was grown at 1100 degrees C, say a native oxide, that will have an etching rate of only 90 to 100 nanometers per minute. So that's a huge difference. That's like a factor of 3 right there, even though chemically both of them are silicon dioxide. Another example is of impurities. So again, you are using 1:1 BHF etchant, and in this case you are trying to etch a silicon oxynitride alloy. So it's there's some amount of oxygen, rest amounts of nitrogen. Supposing this has 7% silicon dioxide and 93% silicon nitride, that would give you an etching rate of say around 35 nanometers per minute. But if you do the same etching with 50% silicon dioxide, which is a much higher concentration, so 50% silicon dioxide, 50% silicon nitride, you will get an etching rate that is 500 nanometers per minute. Now the trend is obvious, the trend is sort of increasing because of more silicon dioxide, and HF etches silicon dioxide faster. So the trend is understandable, but you see the change is humongous. For just 7 to 50% change in composition, you are changing more than an order of magnitude in etching rate. So you have to be a little careful when you are talking about wet etching. In fact, this variability and this controllability is what led people to move towards dry etching in semiconductor fabrication, because dry etching just tends to be a little more reproducible. With that, let us discuss, with those two basic examples out of the way, let us discuss the characteristics of wet etches, especially let us discuss advantages and disadvantages vis-a-vis dry etching. So in general, the wet etch process tends to be very isotropic. That is because it's very hard to find chemicals that have a very profound change with crystal orientation, and also because diffusion plays an outsized role. The advantage of that is that you get very smooth wall profiles. We've discussed that because of diffusion and other things, you tend to get a smooth profile, and isotropic etches tend to give you a more rough profile. This disadvantage is that you have a poor sidewall control. As features in semiconductor fabs have become smaller and smaller, wet etching became out of favor because it was very hard to maintain the very small openings that you are trying to shoot for. Photolithography engineers work so hard to reduce the size of the opening to below 1 micron to below 100 nanometers, and whenever you do a wet etch, suddenly those holes become larger, and that wastes a lot of resources and a lot of effort of the lithography engineers, and that was not liked. The poor side control is also, so it's not just criticality of the future. Sometimes you just want vertical walls. You are doing a microfluidic experiment and you don't want a sloping hemispherical looking shape. You actually want a 90-degree cross section, and it's very hard to get that with wet etch. Supposing you are making a photonic circuit and you have a waveguide, the effectiveness of the waveguide changes whether you have a sloping figure or a rectangular cross section, and rectangular cross sections are preferred, and that is not possible with wet etching. So those kind of things also are problematic. So those are niche applications. The etching rate varies with temperature concentration, we just discussed in the previous slide, and that the advantage is there is a large design space. If you were to spend the time and effort, you can always identify the conditions at which the wet etch does something. The problem is those conditions are very hard to meet. Sometimes the deposition, the range of variation that you can tolerate is so small that for practical cases it's impossible to hit every single time. So run-to-run repeatability, day-to-day repeatability, month-to-month repeatability are all very low. Wet etch process tend to be highly selective. We'll take an example of that when we look at some other recipes in the next lecture. But wet etch recipes, it's not hard to have selectivity of 10,000 to 1, million to 1. And what that, for example, with silicon dioxide and silicon doesn't etch at all. Its selectivity is nearly infinite. And that allows you to do very deep etches for very thin masking layers. So even if the photoresist is only micron, you can essentially go very deep in silicon. Selectivity is not a problem. As you shall see in the dry etches, that can sometimes be an issue, or in an isotropic etches, that can sometimes be an issue. The other great advantage of wet etching is it's a liquid phase process. Practically what that means, you take a wafer, you put it in a beaker, and the beaker has liquid, and the etching happens, and there is no problem at all. A student can learn to do etching within a day. It does not require infrastructure, it's cheap, it's very easy to handle chemicals. If you compare this complexity to what we had to do with CVD, where we had to manage gases, we had to have detectors, we had to have complex pumping systems, wet etching is far, far easier. So when you move from wet etching to say dry etching, where you once again have vacuum chambers, you have plasma, you have design of the plasma, control of the plasma, things become more complicated and more expensive. A dry etching system is worth crores, a hood to do wet etching is worth a few thousand. The disadvantage, however, of the liquid phase reaction is that you tend to have more particulates. It's just a fact of life that gases can be much more purified than liquid. It's very hard to get 6N purity liquids. It's very easy to get 6N purity gases. You also tend to form particulates just because when you're working with liquid, any small amount of particles in the ambient will get into the liquid and form a layer on the liquid, and those particles then tend to stick to wafers when you take the wafers out. Drying becomes tricky. We discussed the part of this is during cleaning, where I sort of emphasize the point that you have to be very careful in drying a wafer after cleaning, otherwise you just get coffee stains. That holds true even when you're doing etching. If you're not careful, you will form coffee stains, and those coffee stains will then create problems down the line. And wet etching always tends to do that, because there's always contamination, there are always byproducts in the solution, and we take the wafer out of the solution, some part of that remains. You can never completely get rid of it. And there are also surface energies issues, especially when you are looking at critical dimensions. Oftentimes sometimes liquid doesn't wet very small features, the liquid is unable to penetrate a nanometer size feature and hence unable to etch. Those kind of problems go away when you're talking about plasma and gas phase, because gas phase by definition can enter small spaces more easily than a liquid can. With that, let me take a step back and talk a little bit about safety. A lot of semiconductor chemicals that we have discussed today, say hydrofluoric acid, we had during cleaning, we discussed sulfuric acid, HCl, etc., are remarkably dangerous chemicals. And you need to be very careful in how to use them. Semiconductor industry has very strict standards on how to use the system, use the chemicals, dispose of the chemicals, etc., and those standards must be followed for your and environmental safety. So in general, when you're doing, say in our clean room, we mandate that when you're managing chemicals, you always have an apron, you always have chemical goggles, you have face shields, you have long sleeve lab coats, you always have gloves, you always have closed-toed shoes. These are non-negotiable. Gloves are, each of these are their own lecture. We actually give a lecture on safety. For example, gloves can come in different types. A lot of people always have access to thin nitrile gloves. These are these examination gloves that you can buy cheaply from a market. However, they are not rated for corrosive chemical usage or hydrofluoric acid usage. They are only rated for general purpose, handling of wafers, or rated for solvents or for biological samples. If you are doing wet etching using aggressive chemicals such as HF, sulfuric acid, etc., please invest in these thick nitrile gloves, which are 2 to 4 mil thick, and they are actually rated for acid bases and toxins. I mean, cryogen is nothing to do with wet etching, but yeah, again, if you're doing cryogenic work, please use appropriate gloves. Different gloves are rated for different things. There is no one glove that protects you from everything. For wet etching work, especially in semiconductor, I would strongly recommend not using latex. Please do not use latex. They are cheap, they are available, but they are not good because they are permeable. Please don't use vinyl. Vinyl gloves are actually for food industry. They are so that people who are cooking do not contaminate the food, but they are not at all rated for chemicals, and they will not protect you from chemicals. And asbestos, again, don't use fabrics, don't use things that create particles. Asbestos has an added problem that it's carcinogenic, so please don't use asbestos. Finally, a topic on hydrofluoric acid. It is by far the most dangerous acid that is probably there inside a clean room and must be given respect. They are very dangerous partly because it's odorless, colorless, so it looks like water. And it looks like water, has the viscosity of water. Often we are using dilute HF solutions, which mostly are water. But it doesn't take a lot of HF to cause a lot of damage. Your body needs to only be exposed at 1%, which is, you can imagine, maybe just small an area on your body, is enough to create an exposure that is potentially toxic, that potentially life-threatening. Okay, so one drop, a little bit of spill is enough to cause a lot of problems. And the worst part is, a lot of times the exposure initially is painless. You don't even know you have been exposed. So that's why those personal protective equipment are so important. They make sure that even inadvertently you don't get exposed. Okay. If you do get exposed, there are some serious things that can happen. For example, you can get decalcification of the bone, the tissue underneath can start dying. These are very excruciating, painful things that can occur. So you use the HF, you got exposed, you go home, you don't realize it, you are sleeping at night, and at night you will wake up to the excruciating pain. It's very, very bad. Symptoms of exposure, for 20%, there are actually no immediate symptoms, so it's very dangerous. But if you see any of these symptoms, please contact your healthcare center immediately. The best, if you do know that you have been exposed, and if the exposure is recent, it can actually be treated very easily. It can simply be treated by writing calcium gluconate gel. The trick is to actually store this in the lab. If you are using HF in your lab, please store calcium gluconate gel as a matter of course. You should always have it, and a lot of it, and if you are ever exposed to HF, please put it immediately. With that, we come to the end of this lecture. In the next lecture, we shall look at more etching recipes and discuss further details of wet etching. Thank you.